Okay.
Oh, for the recording.
Okay, thank you. Good morning, and thank you very much. I'm very grateful to Alexander and Joachim for inviting me to this event. I haven't had a chance to meet Professor Rosenbrock in person, but of course I've heard of him many times, and I read a very interesting biography written by Keith Glover. And what piqued my curiosity in this biography is the book that I didn't know about that Professor Rosenbrock wrote in 1990. So he must have been close to 70 years when he wrote this monograph. And I'd like to read the first sentence of the abstract. I haven't read the book, I must confess, but so there is at present a widespread unease about the direction in which our technology is taking us, apparently against our will. Promising advances seem to carry with them unforeseen negative consequences, including damage to the environment and the reduction of work to the trivial mechanic repetition of actions which have no human meaning. I think as control engineers and control theorists, we cannot be completely indifferent to that issue, because in the end we carry our share of responsibility in the technology that we provide to the world, and we know that this technology is very much under question nowadays. And I'd like to think that my talk is somewhat aligned with what Professor Rosenbrock was raising our attention to. So before I start, I'd like to acknowledge the many collaborators who have worked with me on this topic for the past 10 or 15 years now. Time goes fast. So this includes collaborators, students, postdocs. All of them really made very important contributions to what I will present today. And I'd like to talk today about spiking signals and spiking systems. And my interest in spiking signals comes from the fact that they carry a sort of a mix between the discrete and the continuous, or between the digital and the analog. So on the one hand, a spiking signal is a physical signal. It's typically a voltage that you can measure. So it's analog physical signals. But at the same time, you can count spikes. So there is also something very discrete in these continuous time signals relative to other continuous time signals. And the question that is sort of driving my research is, do we have a theory to compute, to control, to design systems that communicate and exchange information with events, such as spikes? Okay. And really, I think that we are all, the education that we have all received is somehow expressing this, what I'd like to think of the AI gap, which is this big and bigger gap between physics and algorithmics, between the analog and the digital, that on one hand, this is the gap that has made digital technology possible. All the success of digital technology arose from separating the question of computation from the question of how you realize physically the computation. That's very much the task of the computer, that once you program computation on a computer, you can just think of the algorithmics and you don't have to worry about how it is implemented physically. So this was the source of success for 70 years. But I think that today it's also the same separation that is the cause of the fall of the digital age and all the issues that we currently encounter with digital technology. Hence the interest of thinking about something that is in between the digital and the analog. So I do think that there is a problem with digital technology, and I'm sort of just observing that it's now in the news every single day. We hear about the carbon footprint of digital technology. We hear about the fragility of digital systems to cyber criminality. And, you know, we heard just before that the two top priorities of this school, but in fact of any school in the world, is A, to increase digitalization of the society, and B, to achieve a net zero industry. But those two objectives are increasingly conflicting with each other. So I think there is something we need to address there. Of course, I did not invent that. And in fact, it's remarkable that I think Carver Mead was the first scientist to predict that what we are seeing now, and singularly since the pandemics, would eventually happen. So in the mid-80s, he was at the very forefront of CMOS technology. And so he was witnessing that transistors were getting twice smaller and twice faster every year. And he formulated actually Moore's law. But the reason why he formulated this law is that he knew that this would not happen forever. And he became sort of obsessed by the inefficiency of digital machine relative to the animal kingdom. And he became persuaded that the reason why animal computation was so much more powerful and efficient had to do with the spiking nature of communication in animals. So this was really the birth of neuromorphic engineering, and which is now gaining a lot of momentum because of the issue that we are encountering with digital, which of course did not exist in 1990. In 1990, digital was a synonym of free energy. And Carver Mead himself was not alone. In fact, he is one of the three visionary scientists, I think, who created in the early 80s a new course at Caltech. And they entitled this course Physical Computation. So you see that the gap between physics and algorithmics was already occupying their mind at the time. And they foresaw the importance of sort of reconciling physics and computation, and the importance of thinking of new computational models where physics and computation would be much less separated than in the digital computer. Now it's remarkable that what we have on the table today as alternative to digital is one of these three options. So the course existed for 1 year, and then it split it into 3 courses, and over the 80s, Carver Mead started developing what nowadays called neuromorphic computation. Richard Feynman developed the idea of quantum computing, and John Hopfield developed the idea of collective computing. Of course, quantum computing and neuromorphic computing are different from each other. They share the same idea that in order to address the limitation of the digital, we have somehow to entangle the discrete and the continuous. Okay? So that's really a common thread of these two visions of new models of computation. Now, the big difference between the two is that the theory of quantum computation has existed for a century. What we lack is a machine that does that. And with neuromorphic, it's the other way around. The machine has existed since the computer, but we lack a theory. Okay? So what I'd like to talk about today is really what would it mean to develop a theory of neuromorphic computing? Now, the reason why the machine doesn't have to be invented is that it was part of Carver Mead's vision that we don't need a new machine. We just need to use the transistors in a different way. Okay? Now, Carver Mead made the first half of his career was made out of digital computers, so he didn't want to throw that away. But he thought, we can compute differently with the same elements. So we can do spiking computation with digital machines, but it means operating the machine in a very, very different way, and it means working with completely different computational principles. In particular, what the role of the clock in the digital machine is now replaced by the events, and the events are completely asynchronous. They can arise anytime, and you can have an arbitrarily long time between 2 events. And the bits, so the elements of information, are replaced by the spikes that we can count. Now, where do we stand in neuromorphic technology? I think the latest and most impactful advance is the event camera. I will not have time to talk about the event camera, but I think the event camera is really making a revolution in computer vision, and very soon in robotics, and then very soon in control. Okay? And the event camera is a beautiful illustration of what it means to work between the discrete and the analog. You know, we all love our analog cameras, but at the same time we acknowledge that they are not reliable. We all love our digital cameras, but at the same time we acknowledge it's silly to use 1 million pixels to store a photography. And the event-based camera does something in between. It looks like it's incredibly adaptive and dynamic and at the same time very reliable, because the events are discrete quantities. So this was a sort of a long introduction to sort of set up the framework and the motivation why I think there is a huge potential in developing this new way of doing computation. What I will do in the rest of the talk is going to be divided in two parts. So in the first half, I will talk a little bit about where we stand in developing this theory. And there the take-home message is, if you do control, you are in the right home to develop this theory. I do believe that the breakthrough in neuromorphic computation theory will come from control, because I think we are facing a control problem, which I think is a great news for our community. You know, it could be that tomorrow we will be in the very hype of technology instead of being in the shade of machine learning, as we have been for the last 30 years. Okay? And I will try to explain why I do believe that the solution will come from control, because I will try to persuade you that sparking is all about feedback. And I think control is the only discipline where feedback is taken seriously. Okay? The other part of the talk, of course, I will not go technical. I will sort of survey where we stand in the development of the theory. And the second part, I will try to move away from the theory and to answer a very basic question, very concrete question is, assuming that we have a theory of neuromorphic, what should we be doing with it? To what extent should it impact the way we control a DC motor? Okay? So that will be the sort of the two parts of the remaining. Okay, and so to me, at the core of spiking, there is a feedback principle, but there is a sort of a mixed feedback principle. So to me, the current theory of control is a theory of negative feedback, and what we need is just to add a positive feedback loop to create spiking. And so, of course, this is a sort of a very naive vision from a control theorist. You will never hear of that if you go to a meeting in neuroscience or if you go to a meeting in spiking neural networks. But this is my sort of angle of attack. And so I would like to claim that any spiking neural system has that representation, which is very close to the representation of a system that represents to our first-year students. So we recognize the classical feedback loop where we have the plant on the one hand and the controller on the other hand. We recognize the physics of the model. It's a relation between currents and voltage. It could be force and velocity. So it's a physical system. And we recognize the classical negative feedback loop. The only difference with the classical feedback loop that we present in the undergraduate course is the red block. So I have split the controller into something that is monotone and something that is monotone times a minus sign. So that's how I propose to model what I mean by positive and negative feedback. And I will come back to the details of that. But this is sort of the cartoon, right? That's what we present in control classes is what we have on the left. So we use feedback to reduce sensitivity to disturbances. Okay? And the controller is shaping the sensitivity of the system. When we do spiking, it's the same thing for small signal, for small disturbances. The only difference is that if the disturbance exceeds a threshold, we signal the disturbance with an event. So at the core of a spiking system, you have a threshold. Okay? And below the threshold, it behaves like a control system, analog control system. Above the threshold, it behaves like an automaton. It spikes. It sends an event. Hence the mixture of analog and discrete. Okay? It is that simple. And so the spike, the event, is an on-off. It's something very discrete. You don't have something like half a spike. Okay? A spike is a spike. So for a short duration, you open the loop and you just signal that something has happened. Okay? That's the philosophy of a spiking control system. Okay, so how can I make this more concrete? Let me start with an example. And the prototype example of spiking system is a circuit that has existed for a century. It's van der Pol that was later on modified by Fitzhugh and Nagumo to account for the phenomenon of spiking with the simplest electrical circuit. So Fitzhugh and Nagumo proposed this in the late 50s as a response to the big result of the time, which was the paper of Hodgkin and Huxley in 1952, for which they got the Nobel Prize because they came up with explaining how excitability works in nervous systems with the model of an electrical circuit. And Fitzhugh-Nagumo's circuit is just a simplification of the model of Hodgkin and Huxley. Now, we all know this model because we have all studied it in our control class. The circuit has three branches. It has a capacitor, it has a resistive branch, which is nonlinear, and then it has a classical inductive branch. If I remove the inductive branch, I have a flip-flop circuit. I have a bistable circuit. Why? Because the resistor is nonlinear and has a region of negative conductance. So this negative conductance resistor is the key to build a memory. Okay? So with this system, you have a flip-flop. It's a scalar system. It has two equilibrium for one given value of current. So this is essentially how you realize the bit in the computer, if you really go down to the physical realization of the bit. On the other hand, if you remove this resistive branch and only keep the inductive branch, you have a classical RLC circuit that is somehow the essence of control theory. Okay? So it is a system that always goes back to zero, that has fading memory, that is stable, and that you can shape the dynamics of. And so spiking is nothing but putting these two together. You put those two things together, and now you have a sort of a mixture between the flip-flop, which creates the spike, but as soon as the event has occurred, you go back to zero because of the inductive branch. So the difference with the flip-flop is that you have a transient switch as opposed to have a steady-state switch. That's the only difference between spiking systems and a memory system. So spiking is memory at scale. It's memory for a very short amount of time. During the event, the system has memory of the past. Okay? After the event, you forget about the past events. Okay? And of course, the spike is only the first atomic event of many events that you can create by combining events, like you can create words by combining bits. Okay? Okay. And so at the core of a mixed feedback system, you have a threshold. And shaping the sensitivity of a spiking system is shaping the threshold. It's really, and the only way you can shape a threshold is by balancing positive and negative feedback. There is no other way to create a spike. So it is inherently a feedback control problem. So this is the mixed feedback representation of Fitzhugh-Nagumo. So the plant you see is just the storage. It's the capacitor. Okay, I can replace this now with passive systems with any of your favorite physical storage. And the controller, I have separated what provides resists dissipation and what provides negative dissipation. Now you see that in Fitsug-Nagumo, the way you model this negative resistance is just by taking a cubic and then subtracting locally linear terms to create the negative resistance. So for that reason, the separation is very simple. The cubic part is resistive part. The only anti-resistive is these linear terms, this proportional feedback. Okay. So this is clearly providing positive feedback in the system, and clearly both the inductor and the nonlinear resistor is providing negative feedback. Right? So yeah, this is how you can turn this abstraction into something very concrete. And you see that you really need both if you want to create this mixture of memory and regulation. Now, the point that I want to make here is that this picture doesn't just happen for Fitsug-Nagumo. Any circuit that is a spiking circuit. So the spiking circuit means that the voltage that you observe will only be made of events. Okay? Any such circuit has this representation. But now you could think that I is a vector of a 1 million variable, V is a vector of 1 million variable, so it could be a very large network. Okay? And of course I will need to explain what I mean by positive and negative feedback once I have these large networks and once I have dynamics in the system. And we have seen that we need something dynamical because we need something that is fast and something that is slow. You know, I need a hierarchy between first memory, then fading memory. So for this I need dynamics. I cannot build something static that is spiking. And I need something nonlinear, because if you use positive feedback in linear systems, things blow up. So you have no choice. Any model of a spiking must be nonlinear and must be dynamical. And that's why for the last 70 years, those systems have been regarded as nonlinear dynamical systems that have to be studied by neurodynamicists with bifurcation theory, with differential equation, and that has led nowhere. Well, nowhere, it was perhaps extreme. It has led nowhere in giving us a design methodology to build spiking machines. Okay? Okay. So first take-home message is that, you know, spiking systems that look chaotic, oscillatory, nonlinear, whatnot, you should not regard them as, you know, dangerous dynamical systems. They are feedback systems. Very, very close to our language. Okay, second part of the theory, and then I move to the practice. Monotonicity. What do I mean by monotonicity? Monotonicity is the property, the system property that I need for my blocks so that I can talk about positive and negative feedback in this very general framework. Okay? And monotonicity, well, that's the picture, that's the mental picture that we have of monotonicity from high school. A monotone function is a function that has always positive slope at every point. Right? So that's monotonicity. How do we generalize this property for a system that is dynamical, that is nonlinear, that is, okay, that's the question. And there are many ways to generalize the concept of positivity to systems. Okay? But the moment you have this notion of monotonicity, look what you can do. You can analyze these feedback systems the same way we analyze a feedback system in the first undergraduate class. You write the relationships between the input and the output, and you see that if you express the input as a function of the output, so if you compute the inverse system, you have a very, very simple system. Because the first term is the inverse of the plant. I need monotonicity to be invertible. Okay, monotone functions are invertible. Okay? So first pillar property of monotonicity, invertibility. And then you see the passivity theorem, that monotonicity is preserved by negative feedback. Why? Because when you write the input-output relationship, you see that the input is a sum of two monotone functions of the output. Therefore, it's a monotone relation between current and voltage. Therefore, monotonicity is preserved under negative feedback. That's the passivity theorem. Okay? And that gives us a general definition of what negative feedback means. Negative feedback means negative feedback interconnection of two monotone operators. In the linear world, this is negative feedback interconnection of two passive systems. The shearish property of robotics. Okay? Okay, now the red part is I subtract a monotone operator. Here I'm destroying monotonicity. I want to destroy monotonicity because as long as I have monotonicity, I have fading memory. I go back to zero. So I must destroy monotonicity if I want to create the spike. But still, I have a very simple input-output relation, even if it is a 1 million dimension, that the relation between currents and voltage, these spikes, this oscillation, whatnot, is described as a difference of two monotone operators. What are the implications of that? Well, the implication is that it's very physical, because monotonicity is a very physical property, and it's very algorithmic, because I'm going to show that monotonicity is the core pillar of convex optimization. I did not invent any of this, okay? Monotonicity is incremental positivity. So what is the property of positivity that we want to apply to systems if the system is linear? Well, of course, if you deal with circuits, there is a preferred notion of positivity, which is passivity. Why? Because passivity is positivity of the inner product between current and voltage that has a dimension of power. And if you integrate power, so you are saying that the supplied energy to the system is always positive. So passive circuits define those circuits that don't have internal source of energy. It's very physical. That's why you prefer this particular notion of positivity. Okay? Now, monotonicity is incremental positivity. So the only thing that you do to go from passivity to monotonicity is that you replace I and V by increments of voltage and increments of currents. That's the definition of monotonicity that was proposed by Minty, 1960, as a way to define, to generalize passivity to a nonlinear circuit, to a system that, what is a nonlinear resistor? That was the question of Minty. If my system is dynamical, if it is nonlinear, what is the concept of positive conductance? Well, he said monotonicity. And then 15 years later, Rockefeller created the modern convex optimization by observing that the differential, the gradient of any convex function is a monotone operator. So nowadays, if you buy a book about large-scale, state-of-the-art, large-scale algorithm to solve convex optimization problem, it's all about finding the zero of a monotone operator. What does that mean? I mean you want to minimize a convex function. It is equivalent to finding a zero of the gradient. It is equivalent to find a zero of a monotone operator. So we have algorithms at will that solve exactly those equations. Solving this equation for the voltage is finding the zero of a monotone operator if I remove the red part. Okay? Therefore, it's very algorithmic. We have algorithms to solve this equation in millions of dimensions. Okay? I cannot understand why monotonicity has been forgotten in control theory. I studied nonlinear control in the 90s. All the classical textbooks, Isidori, Khalil, whatnot, none of these textbooks mentions the word of monotonicity. A total mystery. Okay, so we have to rediscover the theory of monotonicity that was developed in the 60s and the 70s. So Tom Shafi did a PhD with me on that topic. He studied, you know, all the literature from the 70s, the literature that you don't hear about anymore. Even when I ask people in convex optimization, do you know who invented monotonicity? The answer is always, oh, Rockefeller. No. The concept comes from circuit theory. It comes from physics. It doesn't come from algorithmics. And so Tom Chaffee superbly showed in his dissertation that you can solve monotone circuits of dimension 1,000,000 much faster than by solving a differential equation. And you have splitting algorithms that's exactly, you don't have to invent the splitting as you have to do in convex optimization. Here, the topology of the circuit gives you the splitting. So somehow you can read modern textbooks of convex optimization as an abstraction, as an algorithmic abstraction of circuit theory. But circuit theory is obsolete and it's the ancient times. Okay, now, monotonicity is not enough if we want to describe spiking, like negative feedback is not enough. We need mixed feedbacks. We need this difference of monotone. And in fact, solving a difference of monotone operators is also a well-studied problem, because it's exactly about moving from convex to non-convex. And so there are lots of methods that sort of exploit the fact that you split your operator as a monotone operator. So that's the convex part, and then you subtract another monotone operator. So it's called convex-concave programming. It is a sort of a departure of monotonicity, but of convexity, but a very constrained departure of convexity. We don't want to say, okay, we have a control theory for fading memory, for convex optimization, then we move to spiking, oh, this is an entirely different world, we have to start from scratch. No, we want to leverage all what we have developed for classical control theory and just take the necessary departure from that theory to add this red term, which is this difference of cyclic monotone operator. So the picture is really this one, that as long as you work with monotone operator, not every monotone derives from a convex potential, but so this is a stronger property. It's called cyclical monotonicity. I'm not going to go into the details, but the picture is really that finding the zero of monotone operator is like minimizing a convex potential. And so that's the reason why our theory, our linear theory of circuits is algorithmic. When we move to spiking, we moved from a world of fading memory to a world of memory. So we want to create double well potential. It's deliberate. It's part of the design problem. But we don't want to jump into the unknown of non-convex optimization. We want to create bumps in convex potentials. And each time we create a bump, we create a threshold. So it's a very constrained departure from convex optimization. And it's part of the design problem. Okay, so second part of the message, if you want to take any problem that has been solved through convex optimization in control theory, I'm claiming that you can generalize the solution of the problem to spiking systems by addressing by subtracting what you need to subtract this monotone operator to attack the problem. So this is sort of the angle of attack to develop this theory. And so far, so good. It's working very, very well. And it's all control. It's all control. Okay, now second part of the talk, I want to move to the practical question, which is, okay, assuming that we have a H-infinity theory of spiking, what do we do with that? What should we be using to design our control system differently or not? And so there I want to talk about neuromorphic control. And I think neuromorphic control is a very novel way of controlling a system, but at the same time it's a very classical way of controlling a system. Because any control system, in fact, is a mix between an automaton and a regulation. And again, the distinction between the automaton and the regulation is something that we have created, that is still belonging to this AI gap between the discrete and the continuous. Oh, the automaton, that discrete, the controller, that... I don't think I'm making this up. If you go to Wikipedia and look for the definition of a control system, immediately you have to choose your camp. So for continuously modulated control, you have negative feedback control. For sequential computational logic, you have the automaton. I'm not inventing this. I think we are experiencing that in every single course of control, in every conference of control. It's either a world of automation or it is a world of control design. And those two worlds don't speak to each other anymore. Well, in fact, they have to speak to each other, and that's how they speak to each other. And that is creating material for journal papers, but it's creating a terrible headache for control engineers today. How do we interface those two worlds? And that's what we call the cyber-physical world. This world that interconnects automata and physical systems. And we devote conferences to this topic. Well, we have been doing that for 30 years, because I grew up in the 90s, well, scientifically speaking, and in the 90s, it was the early development of hybrid systems theory. Okay? Now, I've always had a lot of admiration for hybrid system theory, but also I've always been very scared by hybrid systems, because it seems to me that the theory of hybrid systems, you take two untractable worlds and you create an even more untractable world by combining two intractable worlds. Because you sort of add all the difficulties of automata to the difficulties of differential equations. Is this the way to acknowledge spiking? I don't think so. To me, spiking is not the union of automata and it's the intersection. You are extracting from the general world of continuous time signals a very, very special class of signals. Signals that only work with events. Okay? And now you want to acknowledge the specificity of that class of systems, and that's why you develop a theory. You develop a theory to narrow down the theory of differential equation, not to make it bigger. And the promise of neuromorphic, this is really to fill the gap between digital and AI by sort of moving continuously between those two worlds. Okay? And this requires very, very specific types of circuits. Those circuits are the neuromorphic circuits, are the spiking circuits. Okay? Okay, so now I want to, so this is the philosophy, but how do I translate that into something very practical? Very practical. Okay, so can we say anything novel about the control of a pendulum? I think we can say, well, I think I can even offer an open control problem about the pendulum, which is how do we control the things with, I mean, how little energy do we need to control a pendulum? Okay? So, first of all, we need to think of this system as an event-based system. Sensing is event-based. I don't see the motion of the pendulum. I only see events. How do I create events? Well, I put a photo detector, and whenever there is a zero crossing, I have an event. Or I put an accelerometer, and whenever there is a change of sign of change of velocity, I have an event. Very, very easy to extract event, and usually you do that with extremely cheap sensors that cost nothing. Okay? In fact, once you start looking at what we do with our physical sensors, you see that they are all event-based. We just emulate them by having them frenetically clicking so that we can pretend that they measure a trajectory. No, they just measure events. A rate encoder measures events. Otherwise, it's not reliable. Okay? We just want to extract the frenetic side of those sensors and say, but maybe with scarce events, we can do even better than with continuous events. Okay, so now we have put our photo detector, and also that's the sensing, but also the actuation is not going to be a continuous DC motor. It's going to be kicking. Okay, if I want to, that's a kick. Okay, that's a kick. And the kick is a pulse of torque. Again, any actuator is in fact pulsatile. PWM. Again, instead of using the mean fields, the rate implementation, let's use sparse events and see how much we can exploit that. So now we want to close a loop from sensing events to actuation events. And what does it mean to control a pendulum? Well, it means balancing the pendulum at a given frequency and a given amplitude. Okay, does that sound like a reasonable control problem? Okay, so if my amplitude is too small, I need more energy in my kicks. And then, okay, perhaps I can even do full rotation. Whoops. And soon I break it down, so I'm not a good experimentalist, as you can see. But you see the idea. Now, okay, what I'm saying now is that you need to build an automaton first. What is the automaton? The automaton is the controller that will produce the events that you need to balance the pendulum at the desired frequency. So perhaps you are going to choose that the natural frequency of the pendulum is a reasonable nominal frequency because you are not going to use too much energy. And then you set up a clock, okay? And you just need to kick periodically. Well, you need to be able to modulate how hard you kick, okay? So just one pulse, maybe you need a few pulses, and you need to modulate the number of pulses. Okay, so there is a very good automaton that you can create to do this, to balance a pendulum. It's an oscillator, but it's a bursting oscillator. This bursting oscillator has been known in neuroscience for more than a century. It was discovered well before Hodgkin-Huxley, well before people understood how these systems work. But very early in the 1920s, people observed that using nervous circuits to produce clocks is extremely important. Why? Because animals are event-based. And if you don't have internal clocks, you cannot produce events. Okay? So you need fundamentally, and so very early it was discovered that you need a very, very simple structure. You need two neurons that inhibit each other and that have the rebound bursting property. What does that mean? So the neuron A, when it spikes, it inhibits neuron B. So neuron B cannot spike. Now the moment neuron A stops spiking, neuron B has the inhibition released. And as a response to the inhibition, it bursts. Once time, it has a rebound. With that mechanism, you create a clock. Okay? Because they can do that forever, the moment you kick them. Okay? But it's very robust. The bursting frequency on one can be very different. So I don't know how to build a more robust oscillator than this way. Now, this is the interburst frequency is going to set up the frequency of the pendulum, and the number of pulses that I have per burst is going to modulate the amplitude of the kick. So fundamentally, with that automaton, I can entrain a pendulum at any frequency, at any energy. Okay? So that's what I mean by building the automaton of the controller. And you can use this automaton to entrain your system, and you are going to do a very good job. So feed-forward control works remarkably well. Why? Because it's resonance, because it's rhythmic, because anything that is rhythmic, entrainment is a very robust phenomenon. It's used by nature all over the places. Okay, but we don't want to stop there, because otherwise we would lose our job. We want to control the pendulum. So we want to be able to adjust the frequency, we want to be able to change the amplitude, we want to be able to reject disturbances, okay? We want to make the control design insensitive to the length of the pendulum. So that's why we design feedback. So how are we going to design feedback? Phase control. What is phase control? Now you have this bursting clock. You inhibit one of the two neurons with a little pulse of inhibition, and you are going to either delay or advance the next burst. So regulating an automaton is all about timing the events. How do you time the events? How do you do a feedback correction? It's phase control. Phase control is the rhythmic analog of proportional control. Okay? As long as you have an error between the sequence of events that you wish and the sequence of events that you measure from the sensor, you create an error. This error is an event, and this event creates these pulses that are going to advance or delay the phase. Very, very simple. Well, we are not happy with proportional. We also want integral control. Why do you want integral control? Because you want to regulate the frequency and you want to regulate the amplitude of the oscillations. Okay, so we are going to do that with integral control. I'm going to show how to do that. Okay, but with PI, you do a very, very good job of controlling a pendulum. So this is something that we explain in a paper that we have just sent to CDC. I think it's on arXiv, and you will see the details of it. I want to use this sort of a toy example to motivate in the last 10 minutes what I mean by designing the automaton and what I mean by regulating the automaton. And I want to show you that when you do that in a spiking architecture, the two problems are incredibly coupled to each other. It's not at all that you design one thing on one hand, the other thing, and then that you have to combine with cyberphysics. No, it's one and same system, and you use all the time that this system is a mixture of continuous and discrete. And it makes control theory works very, very well. Okay, so now I want to show you how to build this circuit. Because I've shown you how to build a spiker with Fitzhugh-Nagumo, but how do I build this circuit? Well, it's I don't invent this. I'm copying nature. So nature does that with neurons, and every neuron has the same structure. Every neuron has this plant, which is the membrane potential, which is the passive membrane, okay? And then it has current sources. And you can add 1 million current sources to control one neuron. Each current source is providing a little bit of positive conductance, a little bit of negative conductance. I've shown you with Fitzhugh-Nagumo the simplest example where you have two current sources. One is the resistive branch, the other one is the inductive branch. And so one provides negative feedback, the other one provides mixed feedback. Okay? So, and you always need this mixed feedback, so the current source always needs to come in pairs. One positive, one negative, so that you can create a threshold. Okay? Okay, so you can do that with neuromorphic circuits, so you can do that with transistors that consume nothing. Okay, nanoamperes. And that's not what we are doing. We have plenty of labs in the world that are building those neuromorphic circuits and that are pushing the power lower and lower and lower. So you build one spiking neuron with two of these current sources, essentially 5 transistors, okay? And you get a spiking neuron. Now you need to create this bursting neuron. How do you do that? You just copy the mixed feedback motif twice. Because the burst event is an event of events. So you need 2 thresholds. You need one threshold, which is the spiking threshold, but you need a second threshold, which is the burst threshold. And what's the difference between the spike and the burst threshold? Oh, they occur at different amplitude and in different time scales. So the burst threshold is at lower amplitude, because it's going to happen when you inhibit the neuron. And also, it's much slower. Okay, so always dynamics is very, very important. And with just these 4 current sources, you create a rebound burster. Okay? And this rebound burster is very, very tunable. The only thing that I'm going to adjust in this circuit are the maximal conductances of each branch. Okay? I'm going to go back to that later. But I will have, so for this system, I will have 4 parameters. In fact, I will have 3, because the fast excitability is not tuned. So 3 parameters is like PID. Okay, and then I want to build my oscillator. So now I want to interconnect 2. We do that with synaptic interconnection. Synaptic interconnection is again adding another current source, but this time the current source is not dependent on the internal voltage, it's dependent on another voltage. So that's how you can, one neuron can inhibit or excite another neuron. And now I have 2 neurons that still each have this parallel architecture. And with these 2 neurons together, I'm creating this very, very robust. If you build the circuit this way, you can put 30% of uncertainty of any of the parameters. It doesn't destroy the property. You have a feedback mechanism. It's very, very robust to uncertainty. Okay, now you can go from 2 to 200s. And now you can start building an array of neurons. And now you can have a sort of essentially the spatial temporal analog of this very simple clock that I've shown you. But by designing and learning the synaptic conductance and choosing whether you make them inhibitory or excitatory, you can create patterns. And you can create patterns in an extremely, not at all emerging way, in a very, very bottom-up way. Now, why do you need to create this bigger automata? Well, go back to the pendulum. You know, I can control with one kick, but if you look at how children swing, a balance to swing, typically, you know, you have one on each side. So they kick antiphase. Okay? So each of them needs one clock, but the clock needs to be antiphase with the other clock. Or they could also be on the same side of the swing and push synchronously. So now they have one clock and they need to synchronize their clock. And if you do that with 2 children, well, you could do that with 10 motors instead of 1 motor. Why do you distribute? Distributed control. A great way to reduce the energy. So it's very, very easy to distribute this sort of, the architecture of these automata. All what you need is that every single can produce the clock, and then you need to adjust the phase relationship between all the neurons. That's what you do when you design these architectures. And all these systems have this architecture. Okay? So when I put all my neurons together and I collect all the positive and negative conductors together, I end up having this structure. So I can use context optimization to tune, to simulate, whatever you like. Okay. So building the automaton from a spiking architecture is making use of a fundamental principle of nature, which is playing with excitation and inhibition. Okay? And once you have inhibitory principles, you have very, very simple mechanisms to build clocks, to build automata, to build patterns. And that has been studied in neuroscience for 50 years. It's called central pattern generators. It's a very, very good knowledge of how you design those systems. Okay. Now we are not completely happy with designing the automaton. We still want to control the automaton, to make it robust to uncertainty, to make it robust to disturbance, to make it tunable. How do we do that? This is again my mixed feedback system, but now I have acknowledged that the plant is in fact nothing but a bunch, an array of RC circuits. All the storage elements. Maybe 1 million, maybe 200, but it's a big RC circuit. Very parallel, very diagonal. And then I have all the complexity in the controller. And what is the structure of the controller? It's a one-layer parallel neural network. What are the weights? The maximal conductances. Okay? So you have a very, very special type of recurrent neural network, which is nothing but a feedback around a one-layer parallel architecture. Okay? So I think of this as feedback machine learning. But of course, the moment you pronounce recurrence, you cannot use machine learning anymore to tune this, to learn this. What can you do? Well, you can go back to the very old books and you say, oh, but there is this field of adaptive control. How close am I from adaptive control? Adaptive control is you have a plant, you have a controller, and you create a new feedback loop around the controller to adapt the parameters. Maybe I can tune the weights of my neural network with adaptive control. So you need some properties for adaptive control to work. What are the properties that you need? So adaptation is easy. That's what you learn from the book of Astrons in the 70s. You need linear parametrization. Okay? That's good. We have a parallel neural networks linearly parameterized. B, you need a stable inverse, minimum phase. Is my system minimum phase? Oh, this system is chaotic, oscillatory, whatnot. What does minimum phase mean? It means that the inverse system is stable. What is the inverse system? From V to I, I have a difference of monotone operators. Completely stable. And I need a third property. I need relative degree 1 between input and output of the plant. RC circuits are relative degree 1. Nature is ticking the box of what makes design easy. Okay? Any neural circuit that has this architecture is amenable to adaptive control 101. Okay? Okay, so there is a lot of research about this now, sort of digging into the 50 years of adaptive control. Of course, you can do much better than model reference adaptive control. You can do Hebbian learning. You can do, it's very closely connected to Hopfield network. So again, there is a huge literature that you can use, that you don't have to invent, to solve how you tune, how do you do integral control of all these parameters. Okay? So this is how you solve the regulation problem. So you have the design of the automaton, which is just a sort of a bottom-up interconnection of simple motifs. And then once you have the architecture, you have built a circuit that can only do very stupid things. It can only clock with certain phase relationship. And that's your skeleton, that's your automaton that dictates the sequence of events. And the next step is to make this very plastic, adaptive, tunable. And you do that using adaptive control and adaptation of all the parameters. So that's how you combine the design of an automaton and the design of an adaptive controller to do event-based control of a... We haven't done that yet in the lab, but I think it's opening a very interesting sort of open question. How much energy do you need to solve this control problem and to implement it? And the thing is that if you do that with 2 photodetectors and 1 neuromorphic circuit of 4 neurons, probably the amount of computation that you are using is going to cost you, well, close to nothing compared to any form of digital implementation. Okay? So that's perhaps the hope of what we could be doing with spiking control systems. Okay, so I think it's time to conclude. I try to sell you that spiking is, you should not regard these spiking neural networks as very fancy nonlinear dynamical systems. You should regard them as feedback systems. Very, very close to the theory of our field. And the generalization is really a generalization from monotone to mixed monotone. We need to rediscover the importance of monotonicity. That has been done a long time ago in optimization. We still need to do that in control. And then I think this idea of event-based control is really waiting for a theory because it's so natural to control the system with events. And here I want to finish with a very brief mention of who invented event-based control. Carl Aström, him again, wrote a paper in 1991 together with Calvermeet showing how you could use spiking to control the DC motor. This paper today has 35 citations after 30 years. I think it was a genius discovery. Now, 10 years later, someone in Lund, Carl Asen, developed the first event-based PI control. And that got a lot of attraction. That triggered the field of event-triggered control. There was a survey published last year about event-triggered control with millions of papers. It has a section about the history of the field. It starts the history in 1999 with the event-based PI control. So already the connection to the neuromorphic source has been abandoned, has been forgotten. And what the field of event-trigger control has transformed from this idea of having something very energy efficient to a theory of sampling. A theory of when do you have an advantage to sample with events as opposed to do periodic sampling. There is very, very little to gain. So that's why I'm saying we are awaiting a theory for event-based control. Event-trigger control only solves the problem of reconstructing the continuous trajectory from the events and then closes the loop in the conventional way. That's not how we are going to demonstrate the power of event-based control. The power of event-based control is to go from event to event, to shortcut the conversion to digital and the conversion from digital to analog. Okay, I will finish here, and I hope that with this sort of research that I think will happen a lot in our field, we could sort of do one step towards bridging the gap between physics and computation. Thank you.
Thank you very much for the inspiring talk. Professor Sepulchre is happy to answer any questions from the audience. If need be, I am happy to bring the mic to you. Yes.
I can talk like this.
Yes, yes.
I mean, is there, the next step, have you thought about actually then you're talking about electrical circuitry, actually implementing these algorithms ultimately. Do you think actually there is a packing density ultimately in comparison to the digital systems which is higher, or actually is it actually practically then realizable?
Okay, this is a very good point. In fact, for the last 30 years, the design of neuromorphic circuits has been perceived as an analog circuit design problem, translating into a very small community. Because who wants to design analog circuits today? Okay. Now, the future, I think, of neuromorphic is in digital implementation of spiking systems, because ultimately it's not because you implement it analogously that you are going to make a gain in energy. The gain of energy comes from moving away from the frenzy of the clock to the sparsity of events. Events are very rare compared to the frenetic clock of any computer. That is where the energy saving will come from, exploiting sparsity. And it's already underway. So the whole top field of edge intelligence is now, that's the vision, that you bring the intelligence of the sensor much closer to the sensor. And there you use a very, very sparse coding of what your sensors measure. So what you transmit to the computer, the digital will not disappear. It's there to stay. It's just how we use the digital that is crazy. Okay? So we have to use the digital in a much more intelligent way, I think.
Okay. Thank you very much.
Thank you. Any other question?
Thank you for a very nice talk. My question is that when you use adaptive control, would there be issues with the differentiation because there is a spike?
Yeah, that's a good question. The more I work on this, the more I learn that events simplify your life. Okay? Events are never noisy. Okay? An event is an event. So the way we need to close a loop, the only fix that we need to make to the classical adaptive control is that we don't want continuous adaptive control. We want event adaptive control. So only, because the error signal is in itself an event-based signal. So even if you close a loop the conventional way, in fact the loop is open most of the time. Between the events there is no loop. Okay? And so instead of the idea that you have to differentiate, that's somehow what you hear when you go to meetings in spiking neural networks. How do you backpropagation in spiking neural networks? I'm sorry, it's a very silly question to ask that. Because you should never do backpropagation. You should use the events to learn. You should not differentiate the events and pretend that this is a continuous time signal. So events will simplify all the issues that we have had in adaptive control, which have to do with drifting, all of that comes from small signal error that accumulate over time. Here, you avoid that by cutting the loop. And you open the loop only when there is an event.
Thank you. Thank you very much. I'm sure Professor Sepulchre will be very happy to continue answering questions during the coffee break. So please join me in thanking Professor Sepulchre, and I'm sure we can continue the discussion over coffee.